Was there another class before this?
Yeah.
Oh, there's more this time. 5:49? There are more people?
Yeah, there's a lot of people are still picking up.
Everyone that's wearing a hat.
Oh, okay. What does that say? Okay. You'll have to make a shirt like that for this class. What do you think?
Even more ridiculously cool.
Ridiculously what?
No, I just said even more ridiculously cool.
Oh, I see. That'll work. Alright, I guess let's get started. People will trickle in, hopefully. So this is the last lecture. I have a lot to cover, but we don't have to cover any of it, really. This is just to give you an idea of what's going on in the multi-core domain. We've talked a lot about multi-core, actually, in this class. We never necessarily explicitly said multi-core in some cases, but a lot of the concepts we use are applicable to multi-core. And we will see, we'll take a look at how to design some of those cores today and what are the trade-offs related to that. And I'll remind you of some of the fundamental things we've covered in the design of multi-cores and how industry is looking at some of those fundamental things. But before that, you know that there are 2 labs due. Well, lab 6 was due, but we extended the deadline to the same deadline as lab 7. And to clarify, there were several questions. The clarifications were put up on the website, but lab 6, you can turn it in the same date as lab 7, and lab 7 is due May 4, but we give you 2 additional days at no extra cost to you. So you can turn it in on May 6 without any penalty at all, and this doesn't count for your late days. So everybody gets 2 late days, if you will. Does that make sense? So if you don't have any late days, you can still turn it in on May 6 without any penalty at all. Okay? Same as lab 6. Except the difference is the penalty in lab 6, because some people have turned in lab 6 without any penalty. If you're turning it in on May 6th, you'll get a 20% penalty for sure. Okay? Fair? Good. So hopefully this will ease your end of semester. And hopefully you'll enjoy designing or implementing the Magic Cache coherence protocol. And you can actually do a better protocol if you wish for the extra credit. These are lab 6 grades. These are updates actually. There were some things we not misgraded, but many people turned in a little bit late, and we graded them again. So now we have 40 labs, which is good. But that means that 7 people have not turned in their labs, so you still have the opportunity to turn in. And if you're around here, you can do better, much better. Okay? Extra credit. Jason did the extra credit, so he gets his book. Jason had won a book previously, and hopefully this is not the same book that I gave you before. I don't think it is, right?
No, Jason.
Did you get this? Oh, where's Jason? Where's Jason?
It's from the same class.
He always sits over there, right?
Usually.
Okay. Well, he doesn't get his book then. Anybody wants the book? See, this is the misprediction. Locality-based misprediction. You won't get his book though, unfortunately, no. Okay. Well, full credit. We'll see what happens with lab 7. So people who get full credit may get some extra things also. But you should all be getting full credit anyway, right? Actually, I don't know if this got updated. Did anyone else get full credit after that?
Yeah, I would be number 6.
Oh, you would be number 6? Yeah. You want your name there? So Chris didn't tell me that. You can complain to Chris. This is the updated slide, yes. So I updated here. Yeah, it looks like there are more people here now. But this doesn't mean that this is fully correct, because this is quantized, right? So it's anywhere between 2,500 to 2,600. Okay. So final exam, let's talk a little bit about this, because this is the last lecture. It's on May 10th. It's going to be comprehensive. And you know that 3 cheat sheets will be allowed. So you will have a review session at which I will talk about, and this is 30% of your grade. What I would recommend is we'll put up at homework 7 for your benefit to cover the latest concepts. Because this won't be graded, this is just for your benefit to prepare And that'll be up in a couple of days, I think. You'll be busy with the lab anyway until then. So study that for sure. And pass the exams this semester. Definitely know them by heart. All those questions, you should be able to answer them right away, hopefully. Well, some of them will take time, of course, calculation. And relevant questions from the exams on the course website. If you go through those exams, some questions we've already covered, right? And some of homework 7 will actually come from those previous exams. So I would strongly recommend that you study the past exams. And certainly the lecture notes, right? Everything is fair game for the final exam. And we've covered a whole lot of topics. So if you go back, hopefully you'll appreciate the amount of information that you have right now compared to the beginning of the semester. Hopefully it's all exciting. Hopefully it'll help you in the future after the end of this course. Significant. We've covered a lot of fundamental topics that could be useful in many different domains actually, like Amdahl's law, for example. Or things like sequential consistency or coherence. We've covered it within the context of multi-core architectures, but distributed systems have the same issue also. If you design a very large-scale distributed system, like data centers across the world, how do you keep the data consistent, right? If you put your data, if you cache your data, Google, let's say, it has a data center in, well, it doesn't have a data center in China anymore, probably, but it's in Taiwan, let's say, and it has a data center in the US, right? Right? The data is cached. The web indices are cached in different places. Now, how do you ensure consistency? How do you ensure coherence? Same issue at a much bigger scale. Right? In fact, that's the system-level architecture. A lot of the concepts that we discuss are applicable at that scale also. So if you go into industry or if you do research in the future, these fundamental concepts, never forget them. Okay. Anyway, I digressed a little bit, I guess. Review session. We'll have a review session, and I'd like to get opinions on. You want your book? Okay. I'd like to get your opinions on when to hold that review session. So my suggestion would be, I didn't use that book before, right?
No.
Okay, good. Yeah. Now you have more reading to do. That's the burden of doing well. Okay. I propose doing the review session on Tuesday. So we have the exam on Thursday, May 10th, Tuesday, May 8th, and Wednesday is the reading day. Hopefully none of you have exams on that day. That way, if we do the review session on Tuesday, you can study on Wednesday. Is that reasonable to everyone? The question is, what time on Tuesday? Do people have exams?
Not between 1 and 4.
Not between 1 and 4. We know who has an exam between 1 and 4.
Usually before 1.
Say it again?
Early before like early.
Early morning.
How about 10 to 1 a.m.?
10 p.m. Late?
No, not that late. Like 5:30 p.m.
Is 5:30 p.m. reasonable for everyone?
On Thursday?
Yeah. Nobody has exams during that time? You have an exam when? Grade the exams. You can grade them other time. Right? No. Is that reasonable? I can probably do it Wednesday also. But Wednesday evening will be too late, I think. Right. 11 a.m. is probably too early for many people. That's my guess. I'm fine with it, but it's probably too early for many people.
Also, if exams on Tuesday, they probably want to study for that exam on Tuesday morning.
That's right, yeah. That's right. So 5:30?
5:30.
Okay. So let's say Tuesday, 5:30 tentatively, and we'll find a room, hopefully. And come prepared with questions. I don't think I'll have any material to present. And we'll go as long as you would like. I can stay until 1 a.m. if you want. Okay? So come prepared with questions, though. Okay. Anything else related to the exam? Any other questions? We won't have another lecture, so if you have any questions on the exam, okay, you can certainly or come to office hours. Okay, in order on 742, several of you, actually quite a few of you asked me about 742 and research and jobs also. So I'm teaching parallel computer architecture next semester. Is this correct? Fall 2012? Yes. So it's going to be a deep dive into many topics we covered and many topics we did not cover, like systolic arrays we did not cover, which were developed at CMU in 1980s. Speculative parallelization. Can you take a single-threaded program and parallelize it dynamically on a multi-core system, on a multiprocessor system? What are different ways of doing that? Memories. How do you design very large capacity memories? More on data flow. We just scratched the surface on data flow computers, right? Also, we went into multi-threading, but we didn't go into the details of multi-threading. How do you actually schedule the threads in hardware? How do you ensure fairness? How do you ensure high performance? And many more topics. That's in parallel computer architecture. It's going to be research-oriented, so there's no Verilog labs or the labs you have. You could take a simulator like the ones you developed today to explore some of the topics related to multi-threading, for example. You could design new cache coherence mechanisms as part of research, and it's going to be an open-ended research project. And the main topics will be both fundamentals here as well as cutting-edge research topics in the hardware-software interface. So if you enjoy 447 and do well in class, you can take it. If you're interested, definitely talk with me. I know some of you have talked with me already, but I did get a chance to talk with everyone who expressed interest. So that's the purpose of this one. If you're excited about computer architecture research or looking for a job in this area, definitely talk with me. I'd be happy to help you in both cases, research as well as jobs. It's definitely an exciting area, multi-core systems, and with the limits on how much you can scale down the size of a transistor, it's becoming more important to make changes at the architecture level to improve performance, efficiency, and everything else. And we will see some of that today, hopefully. Okay, another important thing, this is the last lecture, course evaluations. Please do not forget to fill out the course evaluations. These are actually very, very important to me. I value this very much. In fact, mid-semester feedback, not a lot of people filled out, but we did take into account your feedback, even though some of it was conflicting. And I read these very carefully and take into account every piece of it, and hopefully improve the course for the future. This is the first time I taught it 447, the undergraduate course, and I'll teach it every spring, hopefully, or every other spring sometimes. And I'd like to definitely improve it based on your feedback. And take the time to write out feedback. There are points where you can pick, and there are also parts where you can write. Right? Well, not handwritten anymore. That's the old times, but you can type if you want. Type out feedback. State the things you liked, topics you enjoyed, and what we can improve on. Tell us what's good or bad, both of them, basically. And I look forward to receiving these. I think these are due May 15th. Is that correct? Okay, that's what I got from one email. But so you still have time, and I'll send you reminder emails on this. Any questions on anything so far? Yes.
So about 742, for undergrads, the prerequisite is 740.
Yes.
So do we really have to take 740 before seating?
So since you've taken 447 with me,
Right.
and if you do well, then you can directly take 742. Because 740 is similar to 447, except it's more advanced. It assumes some things that we covered in this course, and it's more research-oriented. So 740 does not have the very long projects we did in this course. So the incremental benefit of taking 740 would be very low for you. If you take it from me.
Right.
But 740 is also offered next semester, I think, right? That will be a different course because I won't be teaching it. So you should do a talk with Potpourri if you want to take 740 from him. Okay? So graduate courses depend on the professor's style. So I'll do undergraduate courses. And he teaches in a different way than I do. So you will benefit from that. But talk with him. But if you want to take 742, you can definitely take it. You don't need to take 740.
The thing is, OLR does not let us register.
Well, talk with me.
Yeah.
Okay, so if you want to do that, talk with me. Okay. Okay, anything else? Okay, so last lecture, we wrapped up on cache coherence, and this is kind of a summary of the lecture, right? We started with a very simple coherence protocol, valid, invalid, and then moved on to MSI, MESI, OSI, and you can think of other things if you will. And hopefully you know the directory versus snooping trade-offs very well by now. We talked about interconnects, why they're important. We looked at many different topologies, and we stopped on handling contention. Today we'll start with handling contention a little bit, very little, and wrap it up, and then move on to some issues in multi-core, handling serial and parallel bottlenecks better. And I don't know if we will get to it. If we don't get to it, that will be in 742 for sure. Okay, this is not basics, but well, it is basics. So this was the last slide we discussed. We didn't spend a whole lot of time, but when you have two packets, or two messages, if you will, that try to use the same hardware link to go out, they need to be routed this way. And only one of them can go out. You have only a single wire, if you will, that can accommodate a single packet. How do you handle this contention? That was the question, basic question we asked. And you came up with 3 different solutions. You could buffer one of them. You could drop one of them and let the sender, tell the sender to retransmit. Or you could disrupt one of them, right? And these all have different trade-offs, right? So hopefully you can be comfortable with these trade-offs. So if you choose the first one, you need to have buffers. Right? Whereas the other 2 do not require buffers. So in hardware, buffers could be expensive. Because you need to build the buffers, first of all. You need to ensure that buffers do not overflow, which means that you need to have a mechanism to control the flow, or flow control mechanism. Anytime you have buffers, you need to have some flow control mechanism that controls that you don't oversubscribe the buffers, right? And buffers consume static energy as well, right? Static and dynamic energy. You need to write to them. And even if you're not writing to a buffer, it's just leaking. Remember power consumption we talked about? So that's the disadvantage of buffering, if you will. What is the advantage of buffering compared to dropping or misrouting? Any idea? Well, dropping, somebody needs to retransmit, right? Yes?
Saves bandwidth.
Saves bandwidth, exactly, yeah. Basically, in a sense, you're taking out this packet from the network and putting it into the router for a while. You're not keeping the network busy. So it increases your bandwidth in the entire system by having a buffer. Right? You're better utilizing your network. Whereas if you dropped, you need to retransmit. It's like re-execution, right? You're wasting energy, you're reutilizing the bandwidth. Now you may drop it again, right? How many times are you going to drop? Okay? So buffering improves the utilization of the network, it improves bandwidth in the network, so you don't waste it. That's the advantage, big advantage. Disadvantage is more complicated. You need to have buffers, they consume energy, you need to design them so that they work correctly, etc. Dropping, on the other hand, well, advantage is now you don't have buffers, right? The disadvantage is you have to have a mechanism, protocol, if you will, such that when you drop a packet, the node that sent the packet knows that you dropped it, right? So that they can retransmit. And this could be done in different ways. One way is, we discussed, NACking. Once the router drops a packet, it can send a NAC to the transmitter. And the transmitter at that point knows that the packet is dropped. And this is implemented in some protocols. Actually, we discussed some directory protocols that do this, right? Remember that picture that I showed you? Two nodes send a write request to the home node, read exclusive, read exclusive. It's the same thing here, right? Read exclusive. Only one of them can be granted an exclusive read request to a cache block, to the same cache block. And this home node, remember in the picture, sent a NAC saying that, too bad, I cannot grant you a request, send me your request again, later. And there's a design choice, of course. When does this node send the request again? Does it send right away? Does it wait for a while and send it? Those are all design choices. Another way of handling this would have been to buffer the request. That's the first part, right? So NACing is one option. Timeouts is another option, right? You could have timeouts. This node can infer the packet is dropped. That could be harder to design. That's in a sense less deterministic, right? How do you ensure what is the timeout interval? But that's certainly possible based on the design of your protocol. Okay, so that's what you need to do for when you drop the packet. You need to have a mechanism, a protocol to retransmit. Now, when you drop a packet, you also have some issue, right? How do you ensure forward progress in this case? How do you ensure that this node will eventually get its request serviced? With buffering, you don't have this issue, if you will, because you buffer the packet, and the packet will go next time. If you drop, you need to retransmit. When it's retransmitted, the packet can be dropped again. Right? So, forward progress is a bigger issue with dropping. So, that needs to be solved in a dropping-based mechanism. I'm not going to solutions to it, and 742, for example, goes into some of the solutions if you take the course. But that's a fundamental issue that needs to be solved when you drop a packet. That's a disadvantage. Advantage, again, you don't have buffering. It's simpler. Well, it's not clear exactly because now you have to have this protocol, right? At least the hardware is simpler, right? Because you don't have the buffers. The router hardware is simpler because the router doesn't need to have buffers. Okay? The third option, misrouting, deflection. This was the harder one to come up with. It's usually a hard one to come up with. This has been around for a long time, actually. The idea is, actually, we didn't go into too much detail. Let's say you have a mesh that contains a bunch of routers and nodes. So I'll make this a 3x4 mesh. Okay. Let's say this node is sending a message. Let's call this node 0 and node 11. Hopefully. This node is trying to send a message to this node. And that message gets routed through this router here. Well, yeah, let's do it that way. Actually, let's do it perhaps more simply. Let's say the routing algorithm you employ is something called XY routing. The idea in this routing algorithm is very simple. If you want to go through one node to another, the message first traverses the X direction until it reaches the Y coordinate of the destination, and then it traverses the Y direction. Does that make sense? This is called XY routing, or dimension order routing, if you will. Y dimension order, basically you order the dimensions, right? You first traverse the X dimension, that's your routing algorithm, until you reach the Y dimension, and then you traverse the Y dimension. So normally, a packet going from node 0 to node 11 would be routed like this. It arrives in this router. This router says, oh, this packet has not reached its destination dimension yet, so I'm going to route it in the X direction. This router also says, this packet has not reached its destination dimension, Y dimension yet, so I'm going to route it in the X direction. And when the packet comes here, the packet has a destination dimension, which is, I guess, packet's destination is, let's look at the destination coordinate, right? This is 0, 1, 2, 0, 1, 2, 3. So destination of the packet is really 2, 3, right? Is this correct? Yeah. Yeah, destination is 2, 3, and this router itself is at 0, 3, right? So what the router does is it simply compares the y dimension to the destination y dimension, and they're the same. So now I should send it down this way. That's how the dimensional order routing gets implemented. So you can see how simple of a routing scheme this is. So let's say this node is sending a message to this node, and the message arrives here. And at the same time, so this is packet 1, and at the same time, this node is sending a message to this node, let's say, and the packet 2 arrives here, because it does XY routing also. It needs to go this way. Now these two packets, well, I guess I'll fix this. Let's say both nodes are sending a message to the same destination, if you will. In this case, both messages need to go through this link, right? But only one of them can go. Let's say you don't have buffers. Misrouting says send one of them to the destination it wants to go to, and send the other one to the destination it doesn't want to go to. Right? So let's say packet 2 gets the preferred link that it wants to take. It wants to go here. Let's say I change the problem here so that contention actually occurs. Because now both packets need to go to this node, and there's only one link to this node. They collide in this router. And the router can only send one of them. And the router, let's say, picks P2, packet 2. Now what happens to packet 1? There's no buffer. There's no dropping. We're going to misroute it. So how do you misroute it? Well, remember these have backlinks as well, this way. And this is the only link that's used here. So P1, packet 1 can go back, right? The router can say, oh, I cannot route it to toward your destination. Why don't you go back? Does that make sense? Or, the routing, depending on the routing algorithm, the packet can go this way. Right? And then it will get eventually routed to the destination. Let's say the packet went this way. Let's say the router made a choice, misrouted this packet to this link. Now packet 1 is here. It needs to go here, right? So in the next cycle, it'll get routed back, and hopefully this link will be free, and it'll come down. Or another routing algorithm, if you change the routing algorithm a little bit, packet 1 can go this way, right? To this destination. So that's the idea of misrouting. When contention happens, send one packet to its preferable destination, but send the other packet to a destination it really doesn't want to go to. Right? It'll go this way. Does that make sense? So what happened here? If we do this, now we've increased the latency of packet 1. Right? Because packet 1 was trying to go from this node to this node, and the ideal latency, if you will, is 1, 2, 3, 4. It's the minimal latency. Or minimal latency, minimal hop count, if you will. It's really 4 hops. If you misroute or deflect at this node, what happens is you take 1, 2, 3, I guess you could do 4, 5, 6, right? So with deflection, you get 6 hops. And I think that's the best you can do. 1, 2, 3. Assuming no other deflection happens. 4, 5, 6. You could do it that way too, right? Depending on your routing algorithm. So if you deflect, basically your latency increases when you contend. Hopefully it doesn't increase as bad as dropping. And if you buffer, your latency increases also, right? Because you buffer and you wait in the buffer for one cycle at least. So if these links are not busy, deflection, even though it increases latency, now it's utilizing the links better, right? Does that make sense? So you can actually utilize the network better by deflecting. So the upside, now you don't have buffers, and you can utilize the network better. Instead of buffering, you're basically always keeping the network busy. There's no, the packets are always moving. Everybody clear on this? So this has actually been around for a long time. This is called hot potato routing. Have you heard of hot potato routing? It was proposed for the internet a long time ago. And a seminal paper by Paul Baran. It's called On Distributed Communication Networks. I'll abbreviate it. Explains this. It's 1962. And he called it hot potato routing because essentially you can think of the packets as hot potatoes. Right? The router has only a couple of hands, and it cannot hold the potato, hot potato, because it's too hot. So whenever it receives a potato, it's going to pass it on to the next router. If you hold the potato, your hands will burn. And that's holding the potato is really buffering, right? Your hands will burn because the buffers are expensive. You could think of it that way too. So that's the idea of hot potato routing. Advantage, no buffers. Disadvantage, now you take longer routes. There's another disadvantage. Anybody sees that? Yes.
Is it possible that a packet just keeps circling around?
Exactly. Yeah. That's the other disadvantage. How do you guarantee that this packet will reach its destination when there's a lot of contention, right? In this case, my example was there is no other contention, no other deflection that happens. Well, what if your network is so contended that there are lots of packets that are injected by these different nodes, and the packet always gets deflected? This is the same thing as a forward progress or line lock problem. Basically, things are moving, the packet is always moving, but it's never reaching its destination. Right? It's line locked. It's not making forward progress, if you will. It's making some progress, but not necessarily reaching its destination. Okay? So that's the problem with these approaches. Actually, dropping has the same problem. So how do you solve this? Well, you need to somehow impose some prioritization order across packets. Right? So one thing you could do is age order, for example. You could, each packet has a unique number. And whenever contention happens, whenever two packets contend with each other in a router, the packets, the router always deterministically prioritize the packet that has the higher or lower number. That way you essentially form a total order among all the packets in the system, and all routers prioritize the oldest packet, if you will. In that case, the oldest packet is always guaranteed to reach its destination. Okay? So assuming you ensure that, then you're free of line lock. Now the question is, how do you implement it? And if you're interested, you can talk with Chris, because he's developed mechanisms to implement this in a cheap way in on-chip routers with simple hardware. Because if you do oldest, if you need to prioritize the packets based on their age, if you will, or based on a total order, the router becomes complex. Okay? Any questions? So the downside, line lock. That's the other downside. Another downside is now, if there's a lot of congestion, your network becomes full, so packets start getting deflected a lot. So your performance goes down. This is true for dropping as well. When you drop, essentially, you're resending the packets. And if you have a lot of congestion, that's when you actually really drop packets, right? And that's when you get the worst performance also in these mechanisms, dropping and deflection, because contention causes dropping as well as misrouting, and lots of nodes drop and misroute, and lots of nodes are not making a lot fast progress. The advantage of buffering is when the network is really congested, what happens is you have lots of traffic, but the traffic is moved into these buffers, and there's smooth movement from these buffers into those links. So that's, you essentially buy bandwidth, have more bandwidth by adding more buffers. This is not present in dropping or deflecting. Can you have combinations of these mechanisms? Yes, sure, you can have combinations of these also, right? They're not necessarily, fully orthogonal. They're complementary to each other. You can have buffers as well as deflection, right? That's another possibility. Yes?
When you drop a packet, like you let the sender know that you dropped it, but is the sender considered to be the node that actually sent the packet, or the one that it was like if it goes from 0, 1 to 2, is it 0 that's the sender, or the one that immediately just sent it?
So that's a good question. Normally the sender is the one that really sent the packet, because the assumption is that this is the only one that holds the packet, right, to resend. But you can actually design your system such that as the packet progresses, this router, after it sends the packet here, it also holds the packet, right? Normally this is not done.
But wouldn't
You could design a mechanism that way, right?
like doesn't that mean that the acknowledgement itself has to go all the way back to the original sender, which takes a lot more bandwidth than just sending?
That's right. That's right, yes. There's a trade-off there, though. Where do you buffer the packet, right?
Well, if you just had a buffer of 1, then it's not that much more expensive, because it's not like you're not buffering every packet that comes in. You're just buffering the last packet, because all it depends on is the state of the last cycle.
Okay, maybe if you just buffer the last packet, you reduce some of the acknowledgements. But if you're congested again, you'll have the same problem, right? Your buffers need to grow. But you're right. That's when you drop a packet, you essentially need to send a resend message to a node that holds the packet and that can resend the packet. And the question is, where do you actually hold that packet? This node definitely has it because it's waiting for a response. But you could also buffer it earlier. That's one combination, combined mechanism, right? That way you have a small buffer, if you will, here that holds the packet. Maybe not in the router, but somewhere here. Okay? Yes?
Okay, good. So if the packet gets so if you have n hops and it takes n minus 1 hops, and then it can't do the last one, and you have to send it back, then don't you sort of have to guarantee delivery of the pack over n minus 1 things, and then if you can guarantee delivery over n minus 1 things, then it seems like you should just be able to guarantee delivery over n things.
So, yeah, that's the difficulty with dropping-based approaches, NAC-based approaches. Somehow you need to guarantee the delivery of NACs. So NAC networks are usually simpler because it's really a control network, right? It's really one bit that you need to somehow send. But yes, that's a real problem. You need to ensure that happens. That's why a lot of the realistic mechanisms actually rely on timeouts in a higher level protocol. Like internet relies on timeouts, right? When you don't receive a response back, TCP relies on timeouts. And if you don't receive an ACK back in some number of cycles, the node retransmits. Okay. A lot of exciting topics, right? A lot of trade-offs actually related to this, but we will not go into them. Well, hopefully you know the basic trade-offs right now. Okay. Any questions on buffering? Otherwise, we can move to multi-core or more multi-core. Okay, this is not meant to be studied necessarily, but the point is there are many cores that are put on chip today, and you knew this from before. This is just an example slide. And we covered some of the benefits of this, right? Designing a single large core and occupying 1 billion transistors with it is very power hungry. And it's not clear how we would do it, especially if you want to improve the size of the cores, right? Out-of-order execution, we studied in this course. You know why it's not scalable to huge window sizes. And industry now has moved on to putting multiple cores on chip. And a single core cannot exploit parallelism. If your program is parallelizable, right, like if you can divide into many threads, a single core, unless it's multi-threaded, cannot exploit parallelism. Even if it's multi-threaded, if you take 742, you will see that multi-threading is not scalable. You cannot have a single core and have 1,000 threads on it. It's a lot easier to put 1,000 cores, or 48 cores, or 100 cores here, and basically stem them out. Because that way threads are not sharing any resources. So that's the idea of a multi-core. Basically, you have simpler and lower power cores than a single core, and you have many of them. This enables large-scale parallelism, and this could be energy efficient also, as we also studied in another lecture. You remember, you put n cores, you can reduce your frequency by n. Assuming you can perfectly parallelize your program. That way you improve your energy efficiency by n cubed, right? Because the assumption is that you can reduce your voltage by n also. And power has a cubic relationship with voltage, if you will, or frequency. I'll just remind you of this instead of C E squared F, right? If you reduce this by n, then your power goes down by n cubed, right? So that's the advantage of putting these cores. And remember, we said that this works well if you can actually parallelize your program, divide it into n, and get perfect parallelization. But we know that that's not true. So these are just some examples, and these are old examples actually. I cannot keep up with the new things. These are Barcelona and Core i7 from a few years before. Now we did not get into NVIDIA, but NVIDIA calls some things cores. But now that you've taken this course, don't be fooled by this 448 cores. It's not. What they call a core is really a functional unit. So, and functional units are not independent of each other. So, if you call a functional unit a core, then Intel Core i7 has a bunch of cores also, more than 8 cores for sure. So, when you read some of the terminology, just be cognizant of that fact. And if you take 742, we will cover GPUs, and that will become a lot more clear later on. Okay. Anyway, with that aside, with many cores on a chip, what do we want? Well, let's take the case of a single program. We want to parallelize that single program, and we want to get n times the performance with n times the cores when we parallelize that program on n cores, right? Well, that would be great, right? But you know that what we get is really Amdahl's law, right? Well, there's actually another thing here. Should have come there. Well, you cannot do that because of this F. There is a serial portion of the program. So if you put n cores on a chip, you're not going to get n times the performance, unless your F is parallelizing portion is 100%. And even then, if F is 100%, that parallel portion is not perfectly parallel, right? And you know why. You covered synchronization, load imbalance, and resource sharing. So let's take a look at these two different portions. You have the serial portion, you have the parallel portion. Let's assume that the parallel portion is now perfectly parallel for now. We're going to fix that also. But you do have a serial portion. So in a serial code section, what you really want is one powerful large core. Right? You would like to get out of that serial section very fast. But in a parallel code section, if it's perfectly parallel, what you really want is many wimpy small cores. Okay. Maybe a single functional unit even. Okay. And as long as you can parallelize your program on all of those wimpy cores, you still get the same performance at much better power consumption. Okay. So a small core, if you will, or a wimpy core, simple core, and we will see what those are. But you can think of a wimpy core, right? You could have a pipeline core with no techniques that we discussed, like no out-of-order execution, no branch prediction, none of this complexity in the core that tries to improve single thread performance. So parallel code section, you want those wimpy cores. Serial code section, you want a single powerful large core. But the problem is these two conflict with each other. Right? If you have a single powerful core, you obviously cannot have many cores. And, well, why? Because a small core is much more energy and also a small core is much more energy and area efficient than a large core. Right? You may not want to have large cores. So let's take a look at what these small and large cores are. This is just an example. A large core, I'll call large, what that means, powerful. Could be automotive, it could have wide fetch, deep pipeline, aggressive branch prediction, all of the things we've discussed, multiple functional units, memory dependent speculation, what happens with loads and stores. We did not discuss trace cache, but this is one way of supplying many instructions in a single cycle to a wide machine. A small core can be in order, can be one wide, can have a shallow pipeline, 2 stages, 3 stages. Can have a simple branch predictor or no branch predictor, right? Can have few functional units. And this is a good rule of thumb. It's not always correct, of course, but large cores are power inefficient. That part is for sure true. For example, you can get 4x the area, for 4x the area and power, let's assume that way, you can get 2x the performance. It's not always true. But somebody at Intel actually plotted this curve, Fred Pollack, I think, plotted the curve of area of cores over generations and single thread performance. And they figured out that this is a kind of like square root, if you will. As you performance grows with the square root of the area in proportion. So that's a rule of thumb. And this is one other example from this paper that talks about small cores versus large cores. Small core, simple. Large core, more complex, and there's a bunch of other mechanisms. These are normalized performance, if you will. This is a different, a normalized power. This doesn't show the area. So a large core is much more inefficient, but it has much more performance also, right? So if you look at the energy per instruction, it's a lot more inefficient than a small core. But if you want performance, you need this large core. Right? So let's take a look at how industry looked at, designed some of these multi-core engines. Power 4 is one of the first multi-core processors. This is the large part, if you will. IBM has taken the large core approach, and when they put multiple cores, they put fewer and more powerful cores on chip. So they have 2 cores in this first chip, and this is a good paper to look at if you're interested in a real multi-core chip. It's a very detailed paper that talks about how the power core system is designed. And if you look at the core, this employs all of the concepts that you talk about. A lot of auto-order execution in the core. Well, you cannot read this probably, but these are essentially the issue queues or schedulers and many functional units here. Aggressive branch predictors, and this is the reorder buffer. IBM calls it the global completion table, if you will. So just 2 cores, auto-order execution, 108 entry instruction window in each core, 8 byte instruction fetch, issue, and execute. Large local plus global hybrid branch predictor, a large cache, an aggressive stream-based prefetcher. Actually, the stream-based prefetcher that we've discussed in class, a modified version of it was in IBM Power 4. And this is the Power 5, which is the next incarnation of Power 4, except it added multi-threading into it. So if you look at this, I will not go into this detail, but you see that there are 2 program counters, right? 2 instruction buffers from different threads, 2 store queues, 2 reorder buffers, group completion tables, 2 return address stacks. Okay? So this is one example of large core. On the other end, another big company at its time started with very small cores. This is on Niagara. And this was developed around the same time. IBM was a little bit earlier, I think. So if you look at this, you have 8 Spark cores, simple cores, and this is the system architecture. But let's take a look at the core itself. It's simple. It has 6-stage pipeline, It is dual issue. It's in order. There is no out-of-order scheduling. And it has fine-grained multi-threading. There's no branch prediction. There is no interlocking. And it's essentially a fine-grained multi-threaded machine. Fine-grained multi-threading eliminates branch prediction, right? And you can see what fine-grained multi-threading actually adds. This is kind of like your exam question in the first exam, right? You have the iCache, and there are program counters, 4 program counters, and there's a thread select mux that goes into iCache, and there are instruction buffers, and you have 4 register files. There should be a mux somewhere over there, which is not shown here. And there's a thread select logic that selects which thread should go next. And normally, if there are no cache misses, you round robin across the 4 threads. But if you look at the pipeline, it's really simple, right, compared to this, if you will, with all the out-of-order execution. So this is the small core approach. And if you look at single thread performance, what do you have here? I think you fetch from the same thread every 4th cycle. So your throughput is very low, right? Just 1 instruction every 4 cycles. So remember the demands. We want a large core in a serial code section. So we want the IBM Power 4 core, if you will, or something even better. But in a parallel code section, we want many wimpy small cores, many Niagaras. Right? And these two conflict with each other. So let's take a look at what performance you would get with these different approaches. Let's assume that the small core has an area budget of 1 and has a performance of 1 unit, if you will. The large core takes an area budget of 4 and has a performance of 2. This is the tile large approach. And IBM and many AMD and Intel processors take this approach. They have a large core, out-of-order core. In fact, Oracle, I guess, turned around and did the same thing recently also. The benefit is you get high performance on single-thread serial code sections. If you have a single thread, and if you've tiled 4 large cores, you get the performance of 2, right? Because a single thread, remember the assumption, large core takes an area budget of 4, and a performance of 2. This is assuming your area budget is 16. And you've divided your chip into 4 large cores, because each takes 4 area budget. Right? Your performance on a single thread is 2 units. On a parallel program portion, now your performance is bad here, right? Well, not bad, but 8 units, right? What you can do is, let's assume that these are not multi-threaded. You can run 4 threads, and each of them have 2 unit performance, so 8 units. Tile small approach, some other companies have followed this approach. You can tile many of these wimpy cores, if you will, and Tile has tile ultra small, if you will. Those cores are even smaller than the Niagara cores. You get high throughput on the parallel part, right? If you're parallel, you execute 1 thread, and each of them has 1 unit of performance, so you get 16 units of performance. But low performance on the serial part. Now your single thread executes here, and its performance is half the performance of what you would get here. So clearly we don't have the best of both worlds. Right? So what we really want is tile large when we have a serial code section, tile small when we have a parallel code section. So to get the best of both worlds, why don't we have both? That's the idea of heterogeneous multi-core, if you will. And again, this is a very fundamental concept, heterogeneity, if you will. If you have 2 things that are at odds with each other, and if you want to get the best of both worlds, have both of them, and somehow do the right design choice to get the benefits of both. And that's the idea of heterogeneous multi-core. Have both large and small cores on this same chip. And if you look at it, this is an asymmetric multi-core processor. You have 1 large core that occupies 4 units of area, and 12 small cores that occupy 12 units total of area. Now, if you in the serial portion of your program, what happens is you get the performance of this tile large approach, right? You get 2 units of performance. In the parallel portion, you get 12 plus 2 units. 14 units. Because you can execute 2 threads here. Well, the performance of one thread will be 2 over here. Or you can time multiplex down to get 2 performance. Okay. So that's the idea. So how do you actually do this? When you get to a serial code section, that's when you want to run the large core, right? And that's the idea of accelerating serial bottlenecks on an asymmetric multicore. When you get to a single thread, ship that single thread to the large core. If you have this substrate, heterogeneous substrate, let's say this is your single-threaded portion of your parallel program, it executes here. When you go into multi-threaded portion, now the threads execute on the small cores, and when you go back to the serial bottleneck executes here. That's how you can get the best of both worlds. And these are some calculations. This is the same calculation that I did over here previously. With a heterogeneous multi-core, you can get the same serial performance as the large core approach, and almost the same parallel performance as the small core approach. And actually, you can probably tell me how you can move this up to 16. If you actually have multiple threads in the large core, make this 4-way multi-threaded, you can actually get this to 16, if you will. Does that make sense? Okay? Okay. So that's the benefit of a heterogeneous multi-core. This is, you will see this term come up, and more and more portion of the industry are moving into this. Like one other form of heterogeneity, you can think of it from that direction also, but you can have a CPU, if you will, with multi-core, and a GPU on the same chip, right? And they could share the memory hierarchy. That's another form of heterogeneity. Again, GPU-like parallelism, SIMD parallelism, works well here. More serial programs, I would call them. Not exactly, but works well here. The same idea. Get the best of both worlds. Massive parallelism, SIMD parallelism, data parallelism. It's executed here. More serial portions of the code executed here. In fact, this is not a new idea, I would say. Remember the K1 picture that I showed you? Who remembers it? I gave this example several times, right? K1. This was designed circa 1970s, mid-1970s. What did it have? It did have a vector unit, and it did have a scalar unit. Scalar unit was the fastest scalar unit of its time. Right? Vector unit, good for SIMD, data parallel operations. Scalar unit, good for serial code portions. Make sense? It's a heterogeneous processor. Okay. Okay. So let's take a look at how we can take advantage of this heterogeneous substrate even more. It's just, in a sense, it's a no-brainer to execute a serial part of the program in the large core. But what else can you do? Well, we know that there are other bottlenecks in the parallel portion. So can we actually execute some of these bottlenecks on the large core? That's the idea of accelerating parallel bottlenecks. Remember, in the parallel portion, there's serialization that happens as well. When two threads reach a critical section, one of them needs to wait, right, if they're contending for the same lock. Or, we talked about parallel stages that take longer than others to execute. Okay. Why did this happen? You have load imbalance. Remember the example I gave in one of the previous lectures? You have this core 0, core 1, and you divided your work such that this thread takes 1 second to execute, and this thread takes 9 seconds to execute. Now you load an imbalance. You can think of this as the remaining 8 seconds as a serial portion. Because you have not parallelized your parallel parts really well. You have a load imbalance. The idea is Well, why don't you detect that this is the critical thread, if you will, and ship it to a large core? That way you can get better performance in the parallel portion as well, if you have this heterogeneous substrate. Yes?
How do you detect that?
Yes, that's a good question. That's, you can take 742. I'll show you another example, not that particular case, but the critical section case. Okay? But you can think of ways of detecting that. It may be difficult. Another example, we talked about pipeline parallelism, right? Remember, we set up the threads such that they produce, you have core 0 running a thread that produces value for core 1, running another thread that produces another value for core 2. And you can feed in values here, like input values. Let's say you feed in a vector, if you will. And this thread takes in one element at a time, operates on it, and sends it to the next one. Let's say the operations that happen in this thread take much longer. Right? In that case, this becomes a bottleneck. Right? If this becomes a bottleneck, you can detect it perhaps. Right? How do you detect it? That's again a good question. If you detect this, then you can ship this thread to a large core. Right? Because this is your bottleneck in the parallel portion. Does that make sense? Remember the example I gave? You have 3 threads that are communicating with each other. This thread is producing values to this thread, and this thread is consuming those values and producing values for this thread. And you can have a long pipeline that is set up across different cores to do that kind of communication. If one of them is taking long, that's your bottleneck stage. Right? And the bottleneck stage, if you detect this, you can send it to the large core. Yes?
Could you have like a counter in each core which is reset when the execution is done? That way, so that if one thing is still counting, then you can ship it to the larger core?
Oh, yeah, you could do that. You could potentially do that in this case, right? Yeah, you could actually even program it in your program. That's right. So that's one way of detecting it. Here, a way of detecting it is presumably in your program you have queues, right? These are not necessarily hardware queues, but in software, you've written your program such that this thread feeds into a queue, and this thread takes out from the queue. This thread feeds its outputs into a queue, and this thread takes out its inputs from this queue. And if these queues get full, now you know that this stage is not making progress, right? Well, actually, if this queue gets full, right? If your input queue is full, you know that you're not making as fast progress as the previous stage. That's one way of determining it. Then the question is, which queue is the fullest in the system? Right? Okay, so there are ways of determining it. So ideally, we would like to identify these code portions that cause serialization. And serialization is getting to the critical section or taking much longer, one thread taking much longer than the other, and one thread being the bottleneck in this case, and execute them on a large core. So how do we do that? Let's take an example of accelerated critical sections. We've been looking at this for a while. And let me give you another way of motivating the problem that's actually also interesting. So one thing you could do is say, this should not happen. Right? You could take that approach. And some people actually do take that approach. Saying that you really should not have these. Programmer should solve this problem. Okay. Saying that programmer should write programs such that critical sections are not contended. Programmer should reduce the size of those critical sections such that you don't have the serialization problem in the parallel portion. Or programmer should balance the load across these different threads. Or programmer should ensure that this bottleneck thread doesn't happen. Well, then you reduce your performance, right? You still want high performance. So somehow, one approach is to say, programmer, do this. And remember, from the very beginning of the class, there's a fundamental trade-off between programmer and architect. Right? You could do that. That way, if you do that and if you punt on the programmer, this is the right way to go. Right? Because then the programmer should be able to use all those calls and get the best performance, because none of this is true. And even with serial bottleneck, someone can say, that's the programmer's job, right? Again, the programmer should ensure that there is no serial bottleneck. Difficult to do. A lot of burden on the programmer. May be doable, but a lot of burden on the programmer. And software, even debugging software is hard, right? Even serial software is hard. Making it high performance such that you get perfect speed up, I would call it almost impossible. And history has proven that. So that's one non-solution, if you will, at least for the general case. There could be domains where the programmer can actually do that, right? Graphics, for example. But even graphics processors are moving into something like this today. And if you look at NVIDIA's products, there's heterogeneity in their products. Okay, so it's very hard to do. So another way of looking at the problem is synchronization and parallelization is difficult for programmers. Okay? Because of this, critical sections or these bottleneck portions, load imbalance, are a performance bottleneck. So why don't we relieve the programmer a little bit? So instead of putting the same size simple cores, why don't we have a large powerful core and hardware and software cooperatively ship these critical sections to that large core? Serial sections, it's easy. Critical sections, now we're going to try to ship the critical sections to the large core as well. So what is the benefit of this? This reduces serialization due to contented locks, because now the critical section that you're executing executes much faster. Right? So now you can have much better throughput for your critical section execution. This reduces the performance impact of hard to parallelize sections. Right? The programmer needs to write a parallel program. Lock, unlock. It's easier for the programmer to make this bigger, right? Then the programmer doesn't need to reason about what needs to be locked, what needs to be protected as much. In fact, the programmer can start his or her program with a lock, and the thread with a lock, and end it with unlock. Ideally, you would like that. Well, it's terrible for performance. Now you're serializing the threads, right? But if the burden of the programmer is to reduce this size of this critical section, that's what you would like from the programmers ideally, but it's tough to do because the programmer needs to identify what data needs to be protected. And as you push the programmers to actually reduce the size, that's when the bugs happen. That's when the programmer forgets, oh, this shared variable, I forgot to protect it. And now some other thread modified it because it was not locked. And now I get this nasty bug in my multi-thread program that I cannot figure out for, I don't know, months, if you will. So these hard to parallelize code sections, if you ship them to a large core, their performance impact is reduced. Because if you make these critical sections large, then contention increases, right? Now more threads will be in the critical section because critical sections are large. But now if you execute those large critical sections on a large core, now you're actually reducing, improving the performance of those critical sections. Okay? And now the programmer does not need to optimize their parallel code heavily, which means that at least fewer bugs and improved productivity. So let me give you an example of this. Let's say you have 4 threads and they're executing, and this is the critical section. This is the timeline. And let's take a thread 2 at this point, gets the lock, this is the same lock, and goes into the critical section. And nobody contends for that critical section at this time, which is good. But once the thread releases its lock, 3 other threads want that lock, want to go into the critical section. and it turns out based on the policy, thread 3 gets it. Right? So thread 3 enters the critical section, now thread 1 and thread 4 need to wait. They're basically spinning on the lock. Right? And at some point thread 3 releases the lock, now thread 4 gets it, thread 1 is still spinning on the lock, and after some point thread 1 and thread 2 contend for the lock, and after some point thread 2 and thread 3 contend for the lock. So you see that this is the serialization caused by the critical sections, right? Some threads stay idle. That's why you're not getting n times the performance benefit when you have n threads. So what if we magically held the execution time of these critical sections by, let's say, shipping them to a large core? Well, I guess if critical sections execute 2x faster, this is the timeline you would get. So you see that everything executes 2x faster, and there is still some serialization, but it's shorter. And you actually eliminated some serialization here because the critical sections were much faster to execute, so you reduced contention. And I'll let you study this picture, if you will. So accelerating critical sections not only helps with the thread that's executing the critical section, but also the waiting threads. So the waiting threads now wait for less, and sometimes they do not even wait. So what is the downside of these critical sections, if you will? As you add more cores and more threads, the contention for these critical sections actually increases. Right? So this is actually an example from a database application, MySQL. A thread, when it executes, it basically manipulates some tables, shared tables, with between different threads. And it needs to lock the table, and it needs to, well, this is the end of the thread, if you will. It's closing the tables at the end. So it needs to lock the shared table structure and close all of the instances of tables that's kept track, and then it needs to release the lock. Oh. Okay. So if you look at the number of, as you add more threads to this application, this is an online transaction processing application that's running this MySQL database, and this is the chip area, if you will. You're adding more threads, and this is the speed up you get compared to a single thread case. And at 16 threads, if you will, I think this is the 16 point, you get a speed up of 6 times. But after some point, as you add more threads, your performance actually drops. Can anyone guess why? Well, it's this. This is one of the reasons, at least. Actually, if you want to be really sure, it's really all of these. But this is one of the prominent ones in this case. Nope. Basically, what's happening is as you add more threads, or more cores, if you will, all of these cache coherence mechanisms that we discussed, C3. Now this thread is entering the critical section, and it locks, it writes to the lock, it writes to the shared data, and then it releases the data. Now another thread wants that lock. It enters the critical section. What needs to happen? This lock needs to be transferred. And the shared data needs to be transferred. Now another thread enters the critical section. Now we're adding more cores also. This lock needs to be transferred. Shared data needs to be transferred. Another thread enters the critical section. And it happens all transparently with the coherence mechanism, right? And now the lock is there. Lock needs to be transferred. Shared data needs to be transferred. Right? And when you're testing the lock, you need to transfer the lock also, right? It's not only when you're setting the lock. Okay. So that's how and invalidations happen as well on the shared lock, where someone writes to the lock. This lock is a memory location, right? When one of the threads writes to the lock, the cache coherence mechanism sends invalidation to all of the other caches that store that lock. And if you have heavy contention, as you add more threads into the system, more threads are likely to be in this section executing this, and this invalidation traffic increases, your latencies increase, and at some point adding one more thread is not profitable anymore because you increase this traffic a lot more than the benefit you gain from the thread. And that's why your performance starts dropping. As you keep adding, now you lose performance even more. So this is what I mean by limited scalability. Scalability is the performance of your application scales as you add more cores. In this case, clearly that's not happening. So if we could actually, when we get to a critical section, instead of doing this, if we could do something else, which is have a large core here, large core with a big cache, or large cache, let's say. When the thread gets to the critical section, it says large core, execute this critical section for me. Now lock stays here. And large core executes the critical section and sends a message back to the thread saying that, thread, I'm done, keep going with whatever you were doing. Next thread gets to the critical section. It doesn't pull the lock into its cache. It says, large core, execute this critical section for me. Large core executes the critical section for the thread and sends a message saying, thread, I'm done, keep going. Another thread gets to the critical section. This core sends a message, large core executed for me, and large core, when it's done, sends a message back. You get the idea, right? So what's the benefit of this? Now critical sections execute fast because this is large, but there is another benefit. Your shared lock and shared data do not keep ping-ponging between the caches, right? Remember ping-ponging? It just stays here. It's only these messages, which are much smaller, hopefully, that need to get communicated. Well, that's not exactly true, so you should question that right now, but it's mostly true. Yes?
It seems like the processor would have to have a queue of people waiting to have it, and then you have to have like a lock that maintains that. So it seems like you still have sort of money for that lock in the queue.
But that lock also stays there. So I'll show you how this is done. Let me give you the benefit of this first. So if you actually do this, this is what you get on this online transaction processing application. As you add more cores, your benefit still is not high, but your scalability increases. Okay. Okay. So how do you do this? Basically, it's animated by itself. So you have a large core with a critical section request buffer in hardware. That's the queue you're talking about. And this is the critical section. Let's say the critical section is inserting into a priority queue that's shared. This critical section request buffer queues the execution requests from different cores. Let's say processor 2 encounters a critical section. It executes a new instruction called critical section call, and which sends the critical section call request to this critical section request buffer. Processor 1 receives it, and it executes the critical section. And once it's done, it sends a CS done signal, processor 2, and now processor 2 can continue with whatever that comes after the critical section. Make sense? So how can you actually do this? Well, normally what you would have is on the small core, you do some computation, and this is your critical section, and the result is printed somehow, right? So now you need to ensure that critical section receives the data that the small core actually produces for it, and small core also receives the result that's produced by the large core. So there are some modifications to the software, or the locking library, if you will. So instead of just lock unlock, small core, this is the code that runs on the small core, you push the input data into the critical section that's private to this core, and then lock is converted into a critical section call. Do a critical section call for this critical section protected by lock X, starting at target PC. And this request gets sent. So what is sent? The lock address is sent, the target PC is sent, the stack pointer of the thread is sent, and the core ID is sent. And large core essentially queues this request in its request buffer, and then goes into this target PC. And this is what happens in the target PC, essentially the critical section. With some other things, like now we need to actually send the data that's needed by the critical section, right here. So the first thing the large core does is pop A from the stack, because small core pushed A onto the stack, right? And that's needed in the critical section. It then executes the critical section, pushes the result on the stack, releases the lock, and executes a critical section return instruction, which essentially sends a response back to the small core, and now small core pops the result and executes it. Executes the rest. Does this make sense? This is just an example. You could come up with other critical sections this way. But that's how you can accelerate, using a large core, these critical sections. Make sense? Okay, we still have time. Okay. You could imagine other mechanisms of doing this, but the key idea is when the small core gets to the critical section, it sends an execution request to the large core executes it, and it sends a response back. So how does this compare to these different points that we looked at? I will not go into this in much detail, but this is the y-axis is the speed up compared to symmetric tiled small approach, if you will. And it's normalized to hundreds, and these are some multi-threaded applications. These are the MySQL online transaction processing applications, some web cache, spec benchmark, Java benchmark. This is a traveling salesman problem. This is the IP lookup. It's a router application, quicksort, if you will. Actually, this page mine is the histogram example that I've been talking about for a while. A similar one. And yeah, if you look at it, I guess these are the cyan bars. The cyan bars show the performance improvement of shipping the serial section, sequential bottlenecks onto the large core. So you get some performance improvement by doing that shipping. Right? And sometimes you lose performance because sometimes shipping is not a good idea, right? Because there's overhead in shipping also, but not a whole lot. And the darker, the second bars, this is the harmonic mean of the speed-ups, show the performance improvement of accelerating the critical sections, what I just described. So you get 40% performance improvement on average across these applications. And you can actually do more analysis in your applications. It turns out some of these applications are actually written. Programmers put effort into the locks and made the locks fine-grained. They tried to reduce the size of the critical sections. So there isn't as much benefit to be gained in those applications. But there's still quite a bit, right? Applications gained by 20%. Turns out in these other applications, the programmers did not put a whole lot of effort. And these are coarse-grained applications. The locks are larger and there's more contention. So you gain a lot more, like 2.7x, if you will, in terms of performance. So that's the benefit of a heterogeneous multi-core processor that's managed well. So there are performance trade-offs, of course. Let's briefly talk about that. This is not a clear winner in all cases, right? So what happens? Remember we had the multi-core, heterogeneous multi-core. Well, there's still one available here. We divide the chip like this. So, which means that this core is now dedicated for critical sections and the sequential bottleneck. And you're not executing your parallel portion. You cannot use this core. In the parallel portion, you have reduced throughput, right? You have only 12 cores. So now your parallel performance goes down. Right? But your serial performance increases. Right? So it's that trade-off. And Amdahl's law says your speed up is 1 minus f plus f divided by n. Right? Remember? N is the number of cores. And n is these small cores in this case. But now what we've done is, if you will, added something else here, right? We're actually speeding up 1 minus f by m, if you will, compared to a small core. If you add a small core, if you have a large core, it's m times faster than a small core. So we're now speeding up this portion also. Okay, so the trade-off is your n reduces because you're dedicating some of your chipped area for an equal area comparison. Your n reduces because you're dedicating some of your chip area to a large core. But now your m increases as you dedicate more area to the large core. And the question is, how much performance you gain? That's the first trade-off. You're accelerating critical sections or accelerating sequential portions, which means this is increasing. But you have fewer threads in the parallel portion, which means this is decreasing. And it turns out that these results, accelerating critical sections, offsets this decrease. So increasing m offsets this decrease. And that makes sense, right? Why? Because this is your bottleneck. Sequential bottleneck, if you will. Now I've kind of lumped the critical sections over here. But it's the same key inside. And there's also another trend. As the number of cores increases, reducing the number of threads that are available for parallel execution is less important, right? Let's say if you have 1,000 cores, let's say you have 8 cores, 16 cores, and dedicate 4 cores for just single thread performance. And let's think you have 1,000 cores and dedicate 4 cores. Now the loss on parallel throughput is much less if you have 1,000 cores, right? Okay? Because you advertise a loss across many different cores. Okay. So that's one trade-off. The other trade-off is, well, we covered this briefly. Now we've converted this ping-ponging of locks and shared data to locks and shared data do not ping-pong. Instead, when to acquire a lock, you send a message, right? So there's that trade-off. To acquire a lock, you just send a CS call signal, and there's a CS down signal. I guess which one gives you better performance? They avoid ping-ponging of locks among caches by keeping them at the large core. But then that comes at the cost of more signals. And this is something that I thought somebody would say when I said that the only thing you need to send actually is the signal, right? But that's not true. Now what happens is shared data stays here, but any data that's needed by the critical section that's produced by the thread, but that's not shared, needs to be shipped. Right? And that's, if you look back, my example, that's really A here, right? The small core produces A. It's used in the critical section, but it's really not shared data. There's something else that happens in the critical section that works on shared data. So that needs to be shipped. But it turns out that data is smaller usually. So let's take a look at why that's the case. Any questions on the first two parts, by the way? Is it all clear? Yes?
So you have to have a fixed number of critical sections if you do it further, or you just like represent that you're using an address.
So the queue can queue only, well, how many critical sections can be outstanding critical section requests? As many as the number of small cores you have, right? Assuming the small core blocks when it gets to a critical section. So the number of entries in your queue here, the critical section request buffer, is really the number of small cores that can send requests to you. And you could increase it also if you do multi-threading in the cores.
That means the number of queues, not the size of the queue.
Oh, the number of queues? That's only one queue for a large core, right? Or you want to have separate queues for separate critical sections. Yeah. So that. Yeah, you could go. So when we designed this, we had one queue, and there are issues related to it, of course. Now, what happens when you have multiple critical sections? How do you do scheduling?
Yeah.
That's a more advanced concept. We should take 742 for that.
It's almost like you're making a specific local lock. I mean, if you want like all critical sections to run on this core, then now you basically have this.
That's right. So that's the other trade-off, right? That we did not talk about. That's exactly true, right? What happens is if you have multiple independent critical sections that are happening, now they become serialized here. Now there are solutions to that. You could have multiple large cores, for example, or you could have multi-threading in your large core. But let's not get into that right now.
Also, like, where are all the TLBs? Like, does each core have a TLB?
Yes. So the assumption is that all cores are running the same application, so they share the same page table, right?
Okay, but so if I make an access in like at core 3, for example, then I come to the critical section, and then that makes an access. Now it has like a TLB miss.
It could get a TLB miss, but TLBs could be warmed up too, right?
Yeah. And it just seems like you potentially have more TLB misses.
Depends, right? Depends on your working set size and how much your TLB can cover. So in this case, a lot of the shared data stays in the TLB here, right? The translations for the addresses for the shared data. And these could be having other things. So it could go both ways.
Well, especially though if like you have different critical sections, and you have like sets of subsets processors that tend to work only like with one of the critical section. Like now, if this one has to deal with the data from all the critical sections, so like the working size might be small enough such that each subset is.
Yeah, there are definitely cases where you can get more TLB misses, but let's take this offline. But on average, you don't get more TLB misses. But there are definitely cases. It could go both ways, right? You could come up with scenarios that's exactly the opposite of what you said. Okay? Because now you're utilizing your TLBs better. Now your TLBs don't need to cache page table entries for shared data here. Right? Whereas in the previous case, you need to do that. Right? So it could go both ways. And that's actually another trade-off. You're right. You could add that. I guess there are more trade-offs than what I have here. You're right. Okay. So the last trade-off is, you need to ship the private data. So let's take a look at that. This is one example. Is shared data greater than private data? In many cases, actually, private data is smaller. Because what happens is, in this case, for example, let's say you have a priority queue, a heap, that is the shared data, and you're inserting one node to this priority queue, or priority tree heap, if you will. And this is what happens. You touch all of this data to be able to insert this little node, if you will. So you touch many more nodes than the number of nodes you're inserting. So, and cache miss is reduced if shared data is greater than private data. It turns out that's what happens. Okay. And these are some results. You can take a look at it on your own, if you will. So if you look at this, I'll give you a couple of examples, if you will. Now let's take a look at this. So these are some bad cases. As you increase the number of cores, your performance goes down and you cannot recover. And if you shift the critical sections to a large core, this is the performance curve you get. Your performance keeps improving as you add more cores. And that's the case in 7 of these applications. Your scalability improves. The number of threads at which your performance saturates, if you will, at which your performance stops growing, improves. Okay. Any questions on heterogeneous multi-core systems? No? It's pretty intuitive, right? And you could think of generalizing this more, right? The idea is really at a high level, you design your cores not to be homogeneous, because homogeneous is one size fits all. You're trying to fit every single thing to that particular core you design. Whereas if you add heterogeneity into the system, you don't have one size now, you have multiple sizes. The key is, how do you figure out what program fits what size? In this case, what we did was saying, serial sections and critical sections fit the larger core better because they need that performance. More generally, where is this picture that I find for the picture? Oh, it's here. CPU, GPU. Graphics portion of your program fits better. and serial portion fits better. Of course, the portion that doesn't have SIMD parallelism fits better. And you could potentially think of other things, right? I don't know. Some people are thinking of putting with configurable logic, right? That could be another core, if you will. And you could program that as part of your parallel program. And if your portion of your computation fits this better, that's good, right? Or, I mean, existing systems have this, right? Maybe a core for, I don't know, encryption, right? And when you need to encrypt something, you send it to that core. It's a specialized core. Right? A core for encoding and decoding for video. When you need to do encoding or decoding, or video decoding, let's say. This, again, a performance critical thing, if that's what you want to do. Because you need to satisfy the user, right, with a certain frame rate. And that core just does video decoding. It's specialized for that. Remember, we covered the concept of specialization, right? Or special purpose, I should call it. Special purpose versus general purpose. If you have heterogeneous substrates, you can put all of these together. And then the question is, how do you actually use these? How do you program these? And how do you ensure that the right core, or the right accelerator, if you will, that's also another term that people use, is used for the right portion of your computation. So that's the idea of heterogeneous computing in general. And we just covered a special case of it. In fact, your cell phone looks like this, right? You have all these different accelerators. You have a CPU, graphics, video decoder. I don't know if you have encryption on your cell phone, but you have these different chips doing the same thing. And as we can put more transistors on a chip, you integrate all of these on the same chip. So you'll have a big heterogeneous multicore. Even in general purpose systems, I told you that general purpose systems are going the same way also. Maybe we should not go into caching in multi-core systems. What do you think? This is probably a good place to stop the course.
Is it on the final?
Say it again? Is it on the final? It's pretty intuitive. Do you have a shared cache or a private cache? You can answer that question, right? For the final? No. I think let's stop because we have only 8 minutes. So if you really want to go into caching in multi-core systems, I will go into it. But if I don't go into it, it won't be on the final. How about that? If I do go into it, you'll learn about a little caching on multi-core systems, but I don't guarantee that it won't be on the final.
Let's just read the slides ourselves.
What did you say?
Let's just read the slides ourselves.
No, I think let's stop here. If you want to learn more about this is definitely a topic in 742. And certainly heterogeneous computing is definitely how systems are designed today. And going into the future, it will be like this, increasingly so, I think, because we have so many transistors, and you've got to use them for something. And putting a one-size-fits-all core doesn't provide the best performance or best energy efficiency. Well, you talk about performance, but energy efficiency follows the same trends. Okay, well, prepare well for the final, and I'll see you, I guess, at the review session. Thanks.